Hi everyone, in this video we are continuing our discussion on change of variable in multiple integral. We looked at how the change of variable affects the region, how it gets mapped from one region to another. We also looked at how it affects the double integral and that the adjusting factor is the Jacobian. And we looked at a very simple example of finding the Jacobian for polar transformation, which comes out to be R, which is what we expected since we do have the adjustment factor of r dr d theta when we go from rectangular to polar. We look at a couple more examples. Use x equals u squared minus v squared and y equals 2uv to evaluate this double integral where r is the region bounded by the x-axis and the parabolas y equals 4 minus 4x and y squared equals 4 plus 4x. First, let's look at the region. This region will look familiar. It's taken from a problem that we looked at last time. Negative 1 to 0, 1 to 0, 0 to 2, and R is going to be this entire region. Now this problem is sort of backwards in the sense that you're given the substitution, right? So ideally, if you recall, use substitution in single variable, you have to guess what the substitution should be. So that's the most practical scenario. This is a sort of roundabout where, because we've already looked at this transformation earlier, right? This is right here, and it gives this shape, which is why this will work in this case. So this one is just showing you, if you know what the substitution should be, what would the calculations look like. And the next example will give you an example, will show you, if you don't know, then how do you figure out the substitution, right? So here, since it's already given to you, the Jacobian can be found. I'll just write this down one more time. So this will be 2u, negative 2v, this will be 2v and 2u. So this comes out to 4u squared plus 4v squared, which is always greater than 0. So what does our theorem say? Our theorem says, well, integral of y dA becomes the double integral over this new region S of y, which is 2uv, so we have 2uv, then the Jacobian, which is u squared plus v squared du dv. So here you see the adjusting factor is u squared plus v squared, just like the r from polar, and this comes from the oh, I missed the 4 times u squared plus v squared. And how do we know what is the region? We know this is 0 to 1, 0 to 1 because of a prior problem where we know that this maps to 0, 1. And now it's simply a 8 outside, a u cubed v plus uv cubed du dv. So we can do this one at a time. First with the u, we get a 1/4 v plus a 1/2 v cubed dv. So in this step, I did the integration and plugged in 1 and 0. It's easy because 0 will give 0 and 1 will just give 1. So you only have the coefficients here. And the last step, now v becomes v squared over 2. Same story, you will only have contribution by 1 because when you plug in 0, you get 0. So this is going to be 1/8 and a v to the 4 over 4, which gives you another 1/8. So 8 times 2 8s gives you 2, which is your final result. So this is easy because the substitution is given to you. Where this process comes in handy is when you're not given the substitution, right? Which is the next example. So suppose you're asked to evaluate this double integral of e raised to x plus y over x minus y dA, and R is given to be this trapezoidal region with vertices 1, 0, 2, 0, 0, negative 2, and 0, negative 1. So now is where you get to use the power of general substitution. Few observations. First of all, e raised to something, when you're trying to integrate, it's already sort of signaling that this is a little bit different. Next thing, there's a fraction in the exponent of e, and the fraction is not separable, meaning you cannot write this purely in terms of x or y. It's x plus y over x minus y. So something complicated is going on here. And the moment you recognize something complicated is going on, means that you need to do something differently. One of the things that we can do differently is use substitution. Now, if I have to use a substitution here, one of the most obvious substitutions that occur to me is to replace x plus y by u and replace x minus y by v. From here, I can also get the inverse transformation, as x is, if you add these two, divide by 2, and y will be if you subtract them and you divide by 2. So I have a nice way of going from x to y. And I can find the Jacobian of this. Once again, Jacobian is del x, del u, del x, del v, del y, del u, and del y, del v. Okay, finding these are all going to be halves, right? So this is half, this is half, this is half, this is negative half. So this comes out to negative 1/2. Now we need to see what we are mapping here, right? So let me do this in green. The original space we have is a trapezoid going from 1, 0 to 2, 0 to 0, negative 2 to 0, negative 1. So it is this trapezoid shape here. And now we got to figure out under our current substitution, what does each of these sides become? Right, so let's do that. Okay, so first of all, we have y equals 0 and x is between 1 and 2. So u is x and v is x, or we have u equals v. U equals v going from 1 to 2. So that gives me the first structure. U equals v going from 1 to 2 is going to be that goes from 1, 1 to 2, 2 in the UV world. Next one, we have this slant line. I can find the equation of this line. This is x minus y equals 2. So if x minus y equals 2, that's already v equals 2. So v equals 2 means it's a constant line, and u is okay, we got to figure out what happens to u here. Let's see. V is 2 and u is x plus y. Okay, so x plus y here, if you look at the value of x plus y, then u is between 2 and negative 2. At 2 comma 0, right, 2 plus 0 is 2, and at 2 comma negative 2, 0 comma negative 2, 0 plus negative 2 is negative 2. So it ranges from negative 2 to 2. So it's a line that goes across and stops at negative 2, 2. So that's what that maps to. Next we have x equals 0 and y is between -1 and -2. So if x is 0, then we get u is y and v is -y, or u equals -v. So in this case, it simply goes down to the point -1, 1. And this line is x minus y equals 1. So x minus y equals 1 means v equals 1. And u goes from -1 to 1. So this trapezoid gets mapped to another trapezoid, but the new trapezoid is just slightly different. It's not slanted and it appears up there. So now we can rewrite our integral. So over the region R, e raised to x plus y over x minus y, dA becomes over S e raised to u over v, the absolute value of the Jacobian, which is 1/2 du dv. And putting in the limits, u over v, 1/2 du dv, now in the uv world, what happens to u? U, let's go across. U goes from -v to v. And what happens to v? V is restricted between 1 and 2. So the first integral we get, remember the integral of e raised to ax is e raised to ax divided by a. So here, when you do the first integral, this will give you 1/2 on the outside, 1 to 2, e raised to uv divided by 1 over v, which becomes times v. Okay, let me do this again. So you get v e raised to u over v, -v to v. These are limits for u. So when you plug in the values, you get v times e raised to v over v, which is 1, minus e raised to -1. So you have 1/2 e minus e raised to -1, and then a 1/2 v squared, which becomes 4 minus 1. So you get 3/4 e minus e raised to -1. So for these kind of problems, you have to make sure that you do the right substitution. Once you do the substitution, you also have to map the regions out so that you can get the limits and then find the Jacobian and go ahead with that. All right, so the last thing here, which I accidentally mentioned in the previous video, is that this can be extended to triple or 4 integrals by however many variables you have. If you have x as g, uvw, h, uvw, and z is some function of uvw, then this Jacobian, instead of a 2 by 2 matrix now, or 2 by 2 determinant, it becomes a 3 by 3 determinant. Del w, del y over del u, del y over del v, del y over del w, del z over del u, del z over del v, and del z over del w. And the triple integral is substitute Jacobian applying to spherical coordinate. So this is going to be assigned as an extra credit / video verification, video quiz verification, etc., which is just to make sure you're watching the videos. Apply this to spherical coordinate where you have the relation between x, y, and z in the spherical terms. And you know that the Jacobian should be rho squared sine theta, because we have been using that, and this is just another way in which you will end up with the same Jacobian as you should. So you can verify that your answer is correct and then send it across to me. So that's it for this video and this topic. There will be further videos for the upcoming topics.